Hello everyone, and this video is just going to show you an example for temp oscillation. And this example is taken from the textbook. It's a very simple problem, and I also select such type of problem in your homework. Okay, for such type problem, yeah, the strategy is the same. Okay, okay, so this stamp oscillation problem. He says a car is a mass spring system. Okay, the mass is 1,200 kilograms, and your spring is 58 kilonewton. Yeah, be careful, it's kilonewton here, kilonewton per meters. And a sober, okay, a sober is a damping constant, just like I say, the damping parameter, okay, or damping constant. It's called damping constant here. The damping parameter B is 230 kilogram per second. You say after hitting some porthole. Yeah, I'm not quite understand. If you understand, just explain this to me. Okay, maybe just hit the bumpy surface or something. Okay, in the bumpy surface, he said how many oscillation will it make before the amplitude drops into half of its value. Okay, so you just have to calculate how many oscillation after before the amplitude drops to half of its initial value. Okay, so how many oscillation? It says maybe this is just a twist question. It just equal to how much time it has to take for the amplitude drop to half of its initial value. But he used the how many oscillations, but actually it's in fact it is just the basic thing is calculate how much time you need before how much time you need for the input to drop to half of its initial value. Okay. Okay. Let's look. Let's copy the solution here. Okay. The solution for the yeah, we just copy just write some useful formula here. So for damp oscillation, where is my pen? For a damp oscillation, let's start it. For damp oscillation, our amplitude of our solution is, don't forget, is a times term, count times is 2 tau over yeah, minus t, okay, and cosine omega t plus phi. And your omega is equal to omega 0 square minus is b over 2m square, right? B over 2m. Let me check. You can check it one more time. Yeah, b over 2m. Okay, that's our frequency. Just apply. It's just the angular frequency of damp oscillation, and here is the solution of damp oscillation. And in the previous video, I said the tau is called relaxation time, and B over M is the reciprocal of a relaxation time. I think that's all useful information. Okay, then the amplitude drops problem, all we need to care is the decay of the amplitude term. Okay, so we don't have to consider the oscillating term because the envelope of decay here this maybe just temporarily turn this off. The decay of the envelope of the oscillation is follow the exponential function. Okay, so whenever you write the amplitude decay problem, yeah, you don't consider the exponential term. Okay, because envelope of the damp oscillation follow the exponential function. So back to this question. So we have to consider the exponential decay terms. So that means we have to consider this. Okay, we have to consider this term only. Okay, the oscillating term, yeah, we just ignore it. Okay, that doesn't affect our analysis. Okay, he said amplitude dropped to half of its initial value. Okay, so let's see. Let's start calculate this. Okay, so amplitude. Okay, that's for t star with 0. Okay, let's start with t star with 0. Okay, when t star with 0, what's on the amplitude? We just consider amplitude only. So right now I don't consider the oscillating term. So it's a times exponential 2 tau minus 0. So it's just a. Okay, it's dropped to half of its value. Okay, so I don't know the time. I don't know the time, so I call the time. I call the time. I name the time called T1/2. Okay, just time to when this is just the time for the amplitude to drop to half its initial value. But I don't know the time. I name it T1/2. Okay, so it's equal to A times amplitude at T1/2 equal to 2 tau minus 1 times T1/2. Okay, and you say that at the T1/2, the amplitude is dropped to half of its initial value. So it's actually equal to yeah, yeah, initial value is A, right? So half of its initial value, so it's just A/2. Okay, okay, okay. So we reach the equation, and then we will see that actually we don't really need the A, okay, because this will cancel out. So we will have this equation 2 tau minus 1 times T1/2 equal to 1/2. Okay, so we can solve the T1/2 out because do we know have anything? Do we know the tau? Yeah, I think we have the information for tau because we have B, damping parameter, and the mass, so we can get the tau. Okay, but for this equation, how to solve this equation? Just yeah, do not how to do this. Take a log on both sides. Take a log, especially natural log for both sides. 2 tau minus 1 times T1/2 equal to log 1/2. So for this equation, so you have to solve it by your engineering calculator. And the left-hand side actually is very easy. The left-hand side is just 2 tau minus 1 times T1/2. And right-hand side, I think, is minus 0.693, I think. Yeah, that's the solution. Yeah, minus 0.693. And both sides we have negative. Both sides we have negative, so kill it. So what's our T1/2? Our T1/2 is actually 0.9693 times 2 tau. Okay? Okay, what's our tau? Okay, let's calculate our tau. Okay, B over M. Sorry, about it's a bit annoying. Okay, B over M. Okay, so B over M. Do the step. B is 430. Yeah, be careful. It's MKS system, kilogram second. Okay, it's good. M is 1200 kilogram. Let's make sure the unit is MKS system. Okay, kilogram meter and second. So what's our B over M? Or B over M, let's calculate it. B over M is 1200. So let's say it's 0.192. 0.192. Okay, so what's our relaxation time? So B over M is reciprocal of relaxation time. So our relaxation time is actually reciprocal of the 1 divided by 0.192. So it's, okay, let's take three digits. 5.208. That's our tau. Okay, so how many time for amplitude drop to half our initial value? So we have everything we have. So we just put everything in there. It's 0.693 times 2 times 5.208. So what's the time? 5.208 times 2 times 0.693. Okay, it's about 7.218. It's about 7.218 and it's second. Okay, it takes 7.218 seconds for the amplitude drops to half of the initial value. But the problem is asking how many oscillations. So how to calculate how many oscillations? What else do we need? We have this time, but we want to translate how many oscillations. Okay, so I have to I just clean up these things. Okay, so give you time to think. Okay, if you don't have Yeah, I think to cancel this out. Okay, we have time to when the amplitude drop to its half of its initial value, but how do we convert this to for oscillation? How many oscillation? So okay, have you ever figure that out? I just tell you the answers is okay. One period, the one oscillation, doing one oscillation, and doing one oscillation, full oscillation is one period, right? Doing one oscillation means one period. So one period doing one oscillation. Okay. 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 Got this. Okay. Just that simple. So if we have time, so we want to calculate how many oscillation. We just divided just time by period. Okay. One period just doing one whole oscillation, right? So yeah, if we can figure out how many, yeah, the time for doing the time for doing one oscillation, yeah, we can figure out how many oscillation we did in 7.18 seconds. If we understand how many time we have to do for one oscillation. Okay. So do we have any information for the period of this? Okay. So a period, like I say, period. Okay, let's say period. So we can get the from this the omega. Okay, we can get the omega. Okay, we can calculate omega, and omega is something to do with the period. Okay, so let's see. Okay, so the omega is angular frequency. Yeah, frequency and period, they are kind of related to each other. They are related to each other. So if we can get frequency, we can get the period. So what's the angular frequency of the system? Okay, first of all, and we see that okay, we let's calculate. Okay, so the natural frequency of the system. What's the natural frequency of system? Natural frequency actually is equal to square root of k over m. Okay, so so we can calculate this. What's the K? It's 58 times 1 kilo. One is kilo, so 1,000. So and what's the mass? 1,200. So what's the natural angular frequency? So let's do this calculation. 58 1,000 by 1200 and square root. So it's about 6.952. Okay. And also we see, okay, what's the second term? B over 2m. Okay, we already have the B over m. So B over 2m actually is 0.192 divided by 2. And don't forget we have a square. Okay, so square it, we find its value is very, very few. Very, very few. Okay, so if we make the omega zero square, and if you omega zero square minus this value, yeah, yeah, it was like this doesn't contribute that much. So actually, in this system, in this problem setup, actually omega is just equal very close to the natural frequency. So our omega is 6.952. Okay, it's angular frequency, so it's units 1/seconds. Okay, so and then omega t is equal to 2 pi, right? So omega t is equal to 2 pi. So our t is okay. So let's do it. 2 times 3.14 divided by 6.952. So it's 0.903. Our period is 0.903. Okay, one period, one oscillation. Now we have time 7.218 seconds. So how many oscillation? We just divided by the time for the period. Okay, what's the value? Maybe it's not exactly a integer number. 19 divided by 0.903. It's 7.993, 7.99. Yes, maybe let's just call it maybe A oscillations. So just before amplitude drop to half of its value, it will it will you will experience A oscillation. You will experience A oscillations. Okay, so actually it's just a half-life problem, but it want to transfer the half time, the time to reach the half of its initial value and transfer to how many oscillations. So that just the and just using the time and divide it by the time for one period, because one period is doing one oscillation. That's it. Okay. So I just stop video here and see you in the next video. Bye bye. It's a typical problem for demo automation. You'll find many on your homework. Okay, see you. Bye bye. How many time? 15 minutes.